Welcome to our next section over chemical bonding. Now that we know how electrons are arranged in the atom, we can talk about how atoms bond to each other, because it is indeed the electrons that are responsible for that. So, one major important thing we need to know is that atoms are usually not found alone in nature, and most often they are found bonded to each other, and that has to do with their electrical attraction to each other and energy. Okay, so what is a chemical bond? It's a mutual electrical attraction between the nuclei, that's just the nucleus of both the atoms, and the valence electrons of those different atoms that causes them to bind together. Okay, so right here we have a bond. Now, in the middle of this molecule here, there would be a nucleus with protons in it that have a positive charge. And in the middle of this molecule, or this atom right here, there's a nucleus that has protons in it with a positive charge. And each of those nuclei are surrounded by electrons. So these electrons are orbiting their own atom's nucleus, but they're at the same time attracted to the positive charge of the other atom's nucleus. And that attraction to the other atom's nucleus, because of the proton's positive charge, forms this bond between them that causes them to stick together, if you will. So, why do you think atoms usually occur in bonds instead of being by themselves? One of our reasons that we said up above was because of energy. Okay. When atoms are by themselves, they're in a high potential energy situation. Well, high energy is not something that the universe favors, okay? The universe favors low energy situations just like you do. And then here's the example I always use. Would you rather use a remote control to change the channel on the television, or do you want to get up, walk across the room, change the channel, go sit back down, watch the show for a few minutes, get bored of it, get back up, go back to the television, change the channel, sit back down, and have to do that every single time you want to turn the volume up, change the channel, pause it so you can go to the restroom, whatever? Of course you want to use the remote control. That's way less work than having to do it by hand. The universe is exactly the same way. You can also think of this as a roller coaster situation, okay? When an atom is unbonded, it's right up here on top of a hill, we could say, a hill of energy. And it's sitting up there, and it has this really high potential that it could roll down the hill. And so, of course, it wants to do that. It wants to roll down the hill and be at this low energy situation. And that can only happen if it bonds to something else. So if some other atom comes into this vicinity and it gets close to it, then they could both bond with each other, and that reduces their potential energy. And that is something the universe favors, and so that's why bonding happens. Okay, we're about to start talking about electronegativity again, so I just want to refresh your memory on that. We covered the definition for this when we talked about periodic trends, but we're just going to revisit it. Electronegativity was an atom's ability to attract electrons to itself, and remember, it did that by having a lot of positive charge. The more positive charge you had, the more electronegative you were. Okay? So we're going to start talking about the different types of bonding. The first type of bonding we're going to discuss is covalent bonding. Okay? Covalent bonding. Let's break that down. Okay? Co usually means like a partnership. Okay? Valent. Okay? That is talking about valence electrons. Okay, so it's a partnership of valence electrons, and since we're talking about bonding, it's probably between two atoms. Okay, so the valence electrons between two atoms have a partnership with each other. Alright, so here's the simple basic definition right here. When two atoms share electrons with each other, they are in a covalent bond. Okay, so when the electrons are shared, they're in a covalent bond. and that's the main word there, shared. Okay, so each atom is going to donate half of the electrons to be shared into the bond. Okay, and this sharing of the electrons is because of their electronegativity. Okay, so we have a value here for covalent bonds that they range from 0 to 1.67. Okay, if you're going to be covalent, you are no greater than 1.67. This down here is a range of electronegativities, and it decides what type of bond two atoms have between them. Okay, now covalent bonds actually break down into two classes. Okay, you can have a non-polar covalent, or you can have a polar covalent bond. Okay, we're going to talk about that in just a second. On the back of your periodic table that you have in class, you'll see a new periodic table, and it will have a listing of the electronegativities for every single element. So we're going to need that in this section. Mine is different than yours. Mine has only the electronegativities on it. Yours has a lot more information on it. Here's how to help you with that. On your periodic table, you've got a box that's got the atomic symbol in it, and then there's a bunch of numbers on both sides of your atomic symbol. The number that we care about, the one that is the electronegativity, is the top number in the right hand corner. That's the one that we care about on your periodic table, and the one that you're going to be using. Okay, so that's how you locate that. Let's talk about those two classes of covalent bonds. The non-polar. Alright, well, we need to know what polar means. Okay, when we talk about polar in science, we're talking about things being separated onto opposite ends, like a pole, like North Pole and South Pole. And in this case, we're talking about charge. Okay, so if we have a non-polar covalent bond, then that means that the charge is not separated. Okay, in other words, the charge is shared equally between the two atoms. No single atom gets to have the electrons any more than another atom does. So it's, I guess you could say, a perfect sharing, if you want. It is a perfect sharing of electrons. Okay, so atoms that are nonpolar covalent are in the range of 0 to 0.4, and that is their difference. Okay, the difference in their electronegativities. Alright, so it's not what they are themselves, but it's their difference. A handy hint is anytime you have two identical atoms, the difference in their electronegativity will always be 0, which means they're always going to have a nonpolar covalent bond. Okay, so on your periodic table, if you look at carbon here, we want to analyze what kind of bond is there between these two carbon atoms. We're trying to classify it. What kind of bond is that? Alright, well, you have to look at their electronegativities to figure that out. So you look on the back of your periodic table and you see that carbon has an electronegativity of 2.55, and we need their difference. So you say 2.55 minus 2.55 and you get 0. Then you look at your chart here that I've given you, and you see if they have an electronegativity of 0 to 0.4, then we're going to call it a non-polar covalent bond. So this bond here is non-polar. Okay. What about this bond between oxygen and nitrogen? What kind of bond is that? Alright, same thing. We're going to go get the electronegativity for oxygen off the back of our periodic table, and we see it's 3.44. Then you get the electronegativity for nitrogen, and you see it's 3.04. You subtract them, and we get 0.4. Okay, so our range tells us that this must also be a non-polar bond. Okay? In other words, they have a perfect sharing of electrons. The oxygen and the nitrogen share the electrons evenly, and neither of them gets the electrons any more than the other one does. Okay, so now let's talk about a polar covalent bond. Polar, like we said, means there's a separation of charge there, okay? So we're still sharing the electrons. That's true because we're covalent. That means there's that partnership. They're still sharing. But since it's polar, it's an unequal sharing. Okay, so we have this unequal sharing of electrons. Alright, so let's do an example. We want to classify what kind of bond do we have right here. So we go get the electronegativity for hydrogen, and that one's going to be the 2.10. And we go get the electronegativity for oxygen, and that one's this 3.44. We subtract them, and we get 1.34. So if we look in our range here, anything from 0.41 to 1.67 is a polar covalent bond. So this falls within that range. We must have a polar covalent bond right here. Okay. Another note on this, you'll notice that just because hydrogen was first in this little pair up here, it was not the first number. You always do the big number minus the little number. Okay. Alright, let's take a look at this bond over here between carbon and nitrogen. Alright, we go get the electronegativity for carbon, and that one's 2.55, and we get the electronegativity for nitrogen, and we subtract it and we get 0.49. Well, that's in between the range of 0.41 and 1.67, and so again we have ourselves a polar covalent bond. They share with each other, but it's not equal. Here's kind of a picture of what those two situations look like. Here's a nonpolar sharing. See our cloud of electrons here? Notice how they're equally spread out over the two hydrogen nuclei. This is two hydrogens that are bonded to each other, just like that, okay? And so here's the nucleus of one hydrogen with its one proton, and here's the nucleus of the other hydrogen with its one proton, and they each have their one electron floating around outside the nucleus for each of them. Well, when they bond, then those electrons are able to move around both nuclei at the same time, like this, and it's an equal sharing. Alright, well, if you look over here, we have a different situation. We have hydrogen bonded to chlorine, okay? So here's the hydrogen nucleus, and here's the chlorine nucleus, alright? And they each have protons in there. And chlorine has way more protons than hydrogen does. Remember, the more protons you have, the more electronegative you are, because the definition of electronegativity is being able to attract electrons to yourself. So obviously, the more positive charge you have, the more electronegative you are. So chlorine is way more electronegative than hydrogen is, and that causes them to have this polar covalent type of bond. Notice how the electrons spend way more time around the chlorine nucleus than they do around the hydrogen nucleus. I also want to draw your attention to this little symbol here. That symbol, I'm going to zoom in on it, is an S with the tail closed off. And that symbol means partial. Okay, so whenever you see that little S with the tail closed off, it means the word partial. So we have a partially positive hydrogen atom and a partially negative chlorine atom. And that's what polar means. Remember, I told you there was a polar means separation. Let's write that down actually. Okay, right here, let's write in that the word polar means separation. Okay, so the hydrogen doesn't have very many electrons around it Okay? That's what makes it partially positive. Remember, electrons are negative, so if you don't have a bunch of electrons around you, you're going to be more positive. Chlorine has the electrons around it for most of the time, so that's why it's partially negative. The more electrons you have around you, the more negative you are. Alright, this is the second type of bonding. It's called ionic bonding. And in an ionic bond, there is no sharing of electrons. They are completely removed from one atom and given to another atom. Okay, so one or more electrons from one atom are removed and attached to another atom. Okay, and the difference in their electronegativity is going to be anything larger than 1.67. And that's in our little chart down here. So anything above 1.67 is going to be an ionic bond. Alright, here's the question. Do you remember what cations and anions are? We talked about them in the periodic trends section. Okay, hopefully you remember that cations are positively charged ions and anions are negatively charged ions. And remember, an ion is just a charged particle. Okay? So normally atoms are neutral, meaning they have absolutely no charge at all. Okay? But in order to gain stability, they will lose or gain one of their electrons from the valence energy level. And when we talk about stability, we're going to go back to talking about that energy again. Okay, so they're up on this hill and they are waiting to bond with something else so they can move down here to this lower energy level. That's stability, okay? If we can move down here to this low energy level, then they're stable. Alright? Up here at the top, they're unstable. So anytime you see a question or something talking about stability, they're talking about this energy situation, and we need to get to a low energy situation in which the atom is bonded to something else. Okay? Alright. It says right here that they will lose an electron to become a positive ion. Okay? Or they'll gain an electron to become a negative ion. So here's a question. Why would it become positive if it's losing an electron? Can you answer that question? Why would it be positive if it's losing something? I mean, we always think you have to add something in order to become positive. So in this case, why does losing an electron make you a positive? Okay, it's because electrons are negative. And so, if you lose negative things, you become positive. Simple as that. Elements that are described as metallic will tend to lose electrons, and elements that are described as nonmetals will tend to gain electrons. So, where are the metallic elements found on the periodic table? We need to be able to identify them. Alright, we've already seen this picture. We talked about it. We said everything to the left of this stair-step line here was a metal, except for hydrogen. And all the stuff over here to the right of the stair-step line was a non-metal. Okay, so the metals are found to the left of the stair-step line, and nonmetals are found to the right of the stair-step line. Okay, so once they either lose or gain these electrons, then we get a charged atom. Okay, what do we call this charged atom or this charged particle? Well, we had a name for that. What is that? Do you remember? It's called an ion. Remember that? Okay, so which leads us into the fact that this is going to form an ionic bond because we create an ion first. All right, so these charged particles, these ions, have opposite charges, positive and negative, and then they attract to each other, and that's what creates the bond. Here's the order in which it happens, and you do need to know this. Okay, first you lose or gain the electrons. Okay, then a charge forms, and that's when the ions are created, and then that attraction between positive and negative charges is what creates the ionic bond. Most salts are ionic. In fact, I really can't think of any that we'll come across in this course that aren't ionic or ionically bonded. Okay, and notice I said salts. That's plural. Okay, I know that the salt you're most familiar with is table salt, NaCl. I'm sure you've heard that before, but there's a whole bunch of salts. Okay, here's how a salt is formed. Okay, anytime a metal bonds with a nonmetal, you're going to form a salt, and that salt is going to have an ionic bond. Okay, so anytime something from this side of the periodic table bonds with something from this side of the periodic table, you form a salt. Okay, you need to remember that salts are made of metals bonded to nonmetals, and that salts have ionic bonds. Okay, so there's always an ionic bond between a metal and a nonmetal. Here's some differences between covalent bonds and ionic bonds. Okay, so here we have hydrogen and we have oxygen, and they're going to form a bond with each other, and this is the covalent bond. They're sharing the electrons. Okay, now this is probably a polar covalent bond if you looked at their electronegativities, so these two electrons would spend most of their time around oxygen and least of their time around hydrogen, but even so, they are sharing. Okay? Now, let's look at this ionic bond between our metal, sodium, and our nonmetal, chlorine. What happens is chlorine has so many protons in the nucleus, it's like the bully on the playground. It comes up here to this sodium, spots this little electron floating around here all by itself, and it yanks it away from sodium. It completely steals that electron. And when it does it, chlorine takes on this negative charge, sodium takes on this positive charge because it lost one of its electrons, and positives and negatives attract. So sodium sticks around. It's like the bully taking your lunch money and you chase the bully around saying give it back. That's what this is right here. Here's a little bit more detailed picture of that scenario. Notice chlorine has 17 electrons, which means it's also got 17 protons, and sodium has 11 electrons, which also means it's got 11 protons. So chlorine has more positive charge. It gets near the sodium. It steals this valence electron here. Remember, from our periodic trends, we said that the further the electrons get away from the nucleus, the less that positive charge of the protons can pull on the electrons when they're so far away. So it makes them easier to steal. Okay, so this chlorine does in fact come in and steal that electron. Here it is added to the chlorine's valence energy level. So now the sodium is going to be positively charged, the chlorine is going to be negatively charged. Alright? And I also want to make sure that you understand that this sodium right here is completely different from that sodium there. This is actual sodium, the element. It's a shiny, silver looking metal. It is easily bendable. You could cut through it with a plastic knife. It has to be kept sealed under oil because once it reacts with, or once it's exposed to the moisture in the air, it will burst into flame. This is a piece of sodium metal that's been placed into a little container of water, and it's floating around on the surface of the water, and it's burst into flame. That is not the same thing as the sodium ion that you have in your table salt. This is not the same thing as this.
Okay, here we see the sodium going into the water. It floats around on top because of the bubbles it's creating from the heat, bursts into flame, and then it's so violent that you'll see sparks are actually being given off by the sodium metal in the water.
And this chlorine gas is not the same as the chlorine anion. Chlorine gas is actually green, and it is extremely toxic, poisonous. It was used in World War I. It goes by another name of mustard gas. Here we have a soldier with a gas mask, and it looks like two dog companions here with a gas mask on in order to prevent succumbing to this mustard gas. That is obviously not the same thing as the chlorine anion that's in table salt. So please understand that these things are different from each other. That one single electron being moved over from the sodium to the chlorine completely changes it and turns this into salt, and this is that explosive metal, and this is that poisonous gas. Okay? Remember, nature favors using up as little energy as possible, and so in a salt, ionic compounds have to minimize their energy by arranging themselves in an orderly fashion called a crystal lattice. So here are some pictures of a crystal lattice. Here's table salt, and you'll notice that this sodium ion is getting close to this chlorine ion, but it can't get all the way right up next to it because this sodium ion and this sodium ion are both positively charged. And so the closer that this one moves, the more repulsive force it feels from these. Remember, the same charges or like charges repel each other. So yeah, this sodium ion is positively charged and that chlorine ion is negatively charged, and we know that opposites attract, so this sodium ion wants to get closer to that chlorine, but when it tries to, it starts getting pushed away by these sodium ions that have positive charges. Same thing here. This chlorine ion wants to get closer to that sodium, and it wants to get closer to that sodium. But if it tries to, then this chlorine ion and this one start pushing it away. So this crystal lattice arrangement actually happens in this precise way because of all of these pulls and pushes that are experienced by the sodium and the chlorine. They're exactly as close to each other as they can possibly get without being pushed away by another ion in the crystal shape. Alright? As it turns out, table salt's crystal lattice structure is always in the shape of a cube. No matter how big it is or how small it is, it will always cleave in the shape of a cube. So there are these big salt mines called halite mines. And in these mines, minerals grow on the wall, crystals, and those crystals are actually NaCl, table salt. And so they cleave off these big blocks of salt, and then they you can hammer it down. You could put a hammer and a chisel right here in the center and crack this big block, and when you crack it, it'll just cleave into a smaller cube, okay? All the way down to the tiny crystals that are on your table, as you can see here. So from that big block all the way down to regular old table salt, it always forms in the shape of a cube, and that is because of its crystal lattice structure. Now, not all salts will form in the shape of a cube. Their crystal lattice may have different shapes, which cause the actual molecules themselves to form a different type of shape at the macro scale. Alright? Just remember that these ions are attracted to each other, and they're also repelled away from each other, and that is what causes them to arrange themselves at these perfect distances. It's all a balancing act, and now you know why I have an elephant on top of a beach ball. Thank you so much for learning with me, and I will see you next time.